nothing. Not a single response.
Happy Friday.
All right, so I told you last time I might go down and sneak a few pictures of our NMR downstairs, and so here it is. You can see we have our trusty computer, which is connected to our trusty magnet, and so this is what this thing actually looks like downstairs. And so here's a close-up. You can kind of see my reflection in that as I take it. And so the only song I can think of after taking those pictures was Maxwell. Song. All right, so I thought I might do a little review of the all that physics stuff that we talked about last time and see ultimately if we can maybe summarize that into a relatively concise form. And so we saw that nuclei can have spin, and so when nuclei have spin, they also have their own induced little magnetic fields. And so specifically, we're interested in proton NMR, so we'll say that a proton has a tiny magnetic field. And so because of the two spin states, what we can have is when we take our sample, we can see that our nuclei are going to do one of two things. They can either align with our applied magnetic field, or they can align against our magnetic field. So we said that this is our beta state and this is our alpha state. All right, so obviously it's going to be higher energy to oppose our magnetic field, and so that's what we see. We see that the beta state, or the spin down, ends up having the higher energy state. So ultimately, what we can do is we can characterize the differences in energy between these states, and we'll just call that delta E. Now importantly, this is the only reason that we can do NMR, and the only reason it provides us interesting information is that delta E depends on the magnitude of B naught. Basically, how it feels B naught, it tells us what our delta E ends up being, and so for different nuclei in different environments, we end up seeing delta E's. But let's talk about specifically what goes on in one of these experiments. So, in this state right here that I've shown, we are at equilibrium. We said last time that at equilibrium, it's a roughly 50-50 mix of spin states. Which one is slightly more favored? The lower energy or the higher energy? Definitely the lower energy, and so it's slightly higher, slightly a little more of the alpha state. I think we said last time it was about 48 out of a million, so it's a slight favoring of alpha. And so when we do this experiment, what we're going to do is we're going to pulse our sample with some RF radiation. So we'll say that a specific frequency of RF radiation, and it must correspond to our delta E, right? Because a specific frequency corresponds to a specific energy level carried by a photon. And so we have a specific frequency that's going to excite this stuff. And so it is going to excite all of our alpha stuff to beta stuff. So more or less, we pulse this thing, and so what happens is everything gets excited. So we end up with a picture over here. Our energy differences are the same, but now we can see that everything has become beta. All right, so we don't have any alpha now. Considering that we are at equilibrium at this point, and we've excited everything to the excited or the more higher energy beta phase, are we at equilibrium in this picture right here? Does this picture match this picture? It doesn't, and so now we are not at equilibrium. And we're not at equilibrium because everything has gone into the higher energy state, right? So that's not the equilibrium. We know what the equilibrium is. It's about 48 out of a million, favoring the alpha over the beta. And so what do you think is going to happen as this thing returns to equilibrium? What's going to happen to about half of these? Yeah, they're going to fall back down into that lower energy state. And so finally, what happens is our system will return to equilibrium. And so in doing so, a little more, in fact, a little more than half of these will fall back down to the alpha state. And so what we end up is a picture just like our equilibrium. Now, let's think about this. we had to put in some sort of RF radiation at the right frequency to basically go from our alpha to our beta, right? We had to span that delta E gap. And so when we go the other way, what do you think is going to happen? Are we putting in more energy? Or are we releasing energy now? We're releasing energy. And so specifically, what range of the electromagnetic spectrum do you think we're going to be releasing energy on? Well, this delta E we know corresponded to RF radiation, and so delta E didn't change. And so now what's going to happen is we're going to release that RF radiation. And so when we return to equilibrium, our sample is going to emit some RF radiation. And so it ends up being that emitted RF radiation that we're going to measure in an NMR experiment. And so from here, we can measure this. And so what is our x-axis in an NMR spectrum? Parts per million, right? And so that's what ultimately it means by the ppm. The ppm is corresponding to the frequency of energy that is emitted when our system that was excited falls back down into equilibrium. And so we have stuff spanning this delta E gap, and so that's going to give us a specific frequency of radio emission. All right, so this is all fine and dandy, but unless we have different delta E's, each proton is going to end up emitting the same RF radiation because they're going to be spanning the same delta E gap. And so, importantly, we have to answer the question, why do we see different shifts? Why do some protons give us a 3 ppm shift while another gives us, say, a 1 ppm shift? So we'll draw a very relatively crude picture of what this looks like. So again, we're going to have our applied magnetic field, and we'll have it going up. So in our magnet, we're going to have a nucleus. Now, when we have a proton connected in a molecule, there's certainly electron density around that nucleus. And so we're going to just show that with a very crude picture of an electron cloud. All right, so here we've got our electron cloud. And so we said importantly last time, does an electron, all right, so we know that a nucleus has its own magnetic field. Does an electron have its own magnetic field? Does it have spin? We know that it has spin, and so it definitely has its own magnetic field. And so when we put it in this applied magnetic field, is the magnetic field of the electron going to go with B naught or against B naught? Always against B naught. So what we end up with is a little bit of magnetic field in here that's going against B naught. And so essentially, what the magnetic field of our electrons are doing is they're shielding our nucleus a little bit from that overall B naught. It's canceling out a little bit of that B naught. So we have our electron cloud that opposes B naught. And so ultimately the result is that it shields our nucleus from feeling all of B naught. So different protons have different chemical or different electronic environments around them, and so they get shielded differently, and because they get shielded differently, ultimately they end up with different delta E's. And so if they have different delta E's, they're going to have different shifts, right, in ppm. So when we have a shielded nucleus, it fills that B naught less. And so importantly, we will say that shielding is dependent how the electrons what the density of electrons are around our nucleus. Okay, so finally, to summarize all this information into a relatively concise way, we'll say that since delta E depends on B naught, and since different nuclei have different delta E's, we see different chemical shifts. And so in a spectrum, we ultimately are going to measure that in ppm. So now we can see, all right, well, it depends. Basically, we're going to get different peaks based on where our nucleus is in the molecule, because some of them are going to be shielded more and some of them are shielded less. And ultimately, that allows us to distinguish the nuclei in a molecule. And then that ends up I would say this is not a trivial matter. This is a really big deal in organic chemistry. Really, really important. Because before we had to do like a melting point, and this is a little better than melting point. Okay, so we were finishing up class last time, and we were looking at some structures, and we were basically determining how many signals we would expect from a given molecule based on the chemical environments. And so let's do a couple more examples. So let's say we take a look at benzene. So benzene, of course, has one proton of each carbon. So how many signals might you expect for benzene? Yeah, I hear one, and so, I mean, basically it's going to be 1 or 6, right? And so because of the high symmetry in benzene, if we took benzene and we basically rotated it 60 degrees, would we have the same exact picture? Yeah, we would. And so what that tells us is that, sure, all those protons are in fact equivalent. They all have the same chemical environment. And so for benzene, we end up seeing one signal. But again, that's because of that high degree of symmetry in benzene. Those molecules aren't going to have that symmetry. And so let's look at an example. We could say, look at phenol. So phenol looks like benzene, except now we have an alcohol instead of a proton. And so importantly, when we think about this structure, is this bond right here different from this bond right here? Or is it the same? It's the same, right? Because we actually have resonance. And so when we look at the bonds in benzene, do we have any single bonds and double bonds? Or is really everything more like a 1.5 bond? Everything's like a 1.5 bond. So all of these protons are basically bonded to a carbon that has the same hybridization and fills the same amount of electron density. And so when you look at phenol here, how many signals might you expect? All right, so I hear 2, 3, 4. All right, so let's think about it. Clearly, this guy is a lone wolf, right? It's that and there's no other equivalent proton. All right, so let's work ourselves away. Let's call this blue. Now, are there any other protons that are basically one carbon away from this alcohol group? Sure, on the left, right? And so do you think those are going to be equivalent? Yeah, absolutely. All right, so then let's compare this one and this one. All right, so this one is clearly one carbon away from the alcohol. This one is 2 carbons away. Are those equivalent? They can't be equivalent, right? Because they don't have the same connectivity. If they don't have the same connectivity, they're never going to be equivalent protons. So that one is going to be its own signal. Is this going to have basically, will this form a matching pair with another proton? Sure, we've got this one. So ultimately, we can see that both of those are 2 carbons away from the phenol, or from the alcohol. And so finally, we end up with that one there. So how many signals might we expect now that we've disrupted the symmetry in our molecule? Yeah, we would expect 4 different signals. And so that's what we end up seeing in our spectrum. Okay, so we've talked about why we see different signals based on chemical equivalency. So we're going to move right into part B. And so part B is going to briefly talk about signal area. So we get different signals, and so ultimately we can integrate those signals, and we see that that gives us important information. So we'll just say that the area of each peak is proportional to some number of h's. And so importantly, these are relative numbers. You cannot look at a spectrum and determine, all right, there are specifically 3 protons, but you can get ratios between different signals. Now, can we ever have, say, half of a proton? We've always got to have a full proton, and so what that means is that our ratios ultimately all the numbers involved in our ratios must be whole numbers. So always, we must have whole numbers of protons. All right, so let's draw an example of what this might look like. So let's draw a spectrum. So we've got ppm here, and so we start at 0, 1, 2, 3, 4, 5. And so importantly, as we go left on our spectrum here, does that represent more shielded protons or more de-shielded protons? It's definitely more de-shielded this way. so the more de-shielded, or the more amount of electron density that is removed from our proton, the more we expect it to shift to the left. All right, so let's say we see something that looks like this. Let's have one peak, like right here. We'll have another bigger peak right here. Now, just qualitatively looking at these structures, for each signal, we've got two signals. Which signal do you think has more protons corresponding to it? Certainly the big one, right? So we can actually do this quantitatively and pull out really useful information. So the way that this looks is you can use a computer to integrate your spectrum. And so you're going to have this red baseline that moves along here. And so eventually it gets to a peak, and so it integrates that peak. We went a little big, that's it. And then it gets to this peak and it flattens back out because there's no more area being added. And then finally it gets to this other peak and it integrates it again. I'm going to have to go off the page a little bit for size reasons. Okay, and so what we've got is a baseline, and again, your computer has no way of knowing how many protons you've actually got in your molecule, but it does know that it can integrate these peaks. And so what you could end up seeing is, say, it says, all right, your area is 25. It's just going to spit out a number at you and say 25. And then it's going to take a look at the difference here, and it's going to say, well, clearly that is bigger, and so that's 75. All right, now when we draw organic molecules, certainly we can have them. We could have a molecule that has 100 protons, but probably not. Typically, we're working with smaller molecules that don't have that many protons. So we see this ratio of 25 to 75. What's the simplest ratio that could actually be corresponding to? Yeah, it could be 1 to 3. What else? It could be 2 to 6. It could be 3 to 9. And so there's no way without more information for us to know what that actually corresponds to. So fortunately, in cases like this, you'll often know the molecular formula, right? And so in this case, our molecular formula is going to be C5H12O. And so of those three ratios that I've listed, which do you think is the actual ratio? Well, how many protons are in our molecule? 12. And so we know that these numbers are going to have to add up to 12. And so we know that it's the 3 to 9 in this case. So basically, what you're going to do, you're going to see how many protons you've got, you're going to take your ratio, and you're going to make sure that it adds up to that number of protons. So in all cases, what you should see are whole numbers here. You're never going to have a ratio of like 1.5 to 4.5. We can't have half protons. And so a molecule that would make sense for this would look like, if we had a methyl, and methyl there. So clearly, the 3 protons on this methyl group are going to correspond to this signal right here. Does it make sense that this signal would be more de-shielded? Sure, right? And we'll talk about that more in a minute, but you can see this is directly next to an oxygen, and so that oxygen is going to be sucking electron density away from those protons, and so it's going to be pretty de-shielded. And then we've got the other 9. Are these all equivalent? Yeah, these are definitely all equivalent. So we can see those are further away from the oxygen, and so they're going to be more upfilled, more shielded, and so they end up being there at 1. All right, so we've got 2 signals expected from this molecule. And so not only do we see separate signals, but those signals are going to have areas, and we can determine what the ratios of protons are from those areas. All right, that's all we're going to do with peak area. So we'll move now into chemical shift. What are the characteristic chemical shifts that we see in molecules? And so, of course, the chemical shift depends on how shielded. And what's doing the shielding? Electrons, right? So it's the magnetic field of electrons. So how shielded by electrons a nucleus is. So we're going to focus in on 2 characteristic effects that we end up seeing. So one of them is going to be the inductive effect that we've talked a little bit about already with polarity. So 2 main effects. One will be the inductive effect. Bless you. And we'll also see that pi bonds have an effect. And the pi bond effect is pretty weird. We'll talk about that for a few minutes. All right, so we're going to jump first into the inductive effect. I think that one's more straightforward. This one's a lot more intuitive. And so for the inductive effects, let's remind ourselves that here we've got ppm. So going left is going to be more de-shielded, which means going right, we're going to have protons that are more shielded. And so if we consider inductive effects and how electronegative atoms near protons affect them, it's going to, the reasoning is easy. So inductive effects. So we're just going to look at some trends. And so we'll compare 4 molecules first. So let's compare this molecule, and so we're focusing on those protons, not the OH proton. We will talk about bromine, and then we'll just talk about methane. And so, of course, in that place, we've replaced our group with just another proton. All right, so of these 4 sets of methyl protons, which do you think is going to be the most de-shielded? Well, what's causing the de-shielding in the first place? It's going to be the pulling of the fluorine, right? The fluorine is pulling the electron density away. Basically, in effect, it is de-shielding the protons over there. It's removing that electron density that would buffer those protons from filling that B naught. And so as we move left to right, clearly this dipole is going to get bigger or smaller. It's going to get smaller. And so where are we going to see the most de-shielding? Is it going to be on the left side or the right side? Definitely the left side. So on the left side, we see more de-shielding. And so if we do this NMR experiment, what we end up seeing is a shift here of about 4.3 ppm. As we work our way left to right, as we decrease the polarity of these bonds, we see that our protons become more and more shielded. And so we go from 4.3, this backs down to 3.5 ppm. 2.7 ppm for bromine, and then 1.0. So this is what we would expect knowing what we do about bond polarities, right? So the less polar our bonds are getting here, basically the more shielded our protons become, and so they move to the right. They become more shielded. All right, so that's one trend. Another trend is how many electronegative atoms are nearby our proton, and so in chloroform has a structure that looks like this. We could also have dichloromethane, and so that looks like this. And then we'd have chloromethane, so chloromethane looks like this. And so of these 3 molecules, 1, 2, and 3, which do you think is going to have a proton that is the most de-shielded? Again, it's going to be the one on the left, right? Because over here we have 3 chlorines that are pulling electron density away, and on the right side we just have 1 chlorine. And so, yeah, that's exactly how it matches up. We end up seeing chloroform way downfill, about 7.3 ppm. Dichloromethane is about 5.3, and the chloromethane is back to about 3.1. Okay, so certainly the number of electronegative atoms near our protons makes a difference. So then finally, do you think the distance between an electronegative atom and our proton makes a difference? Sure, it definitely does in the inductive effect, and so that's again what we end up seeing. So let's just look at one molecule. So we'll have a methyl group, CH2, CH2, and then chlorine. So how many signals would we expect? We would definitely expect 3 signals. Clearly the methyl is a terminal CH3, and so there's nothing else like that. Here we've got a CH2 connected by carbons. Here we've got a CH2 with a chlorine on the side. So the connectivity is different for all 3 of these sets of protons, so we would expect 3 signals. Which protons do you think are going to be de-shielded the most, A, B, or C? Definitely C. So what we would find is if we did an experiment on this would be about 3.3 ppm. The next methylene would be about 1.6, and then our methyl group is about 0.9. And so what we're able to do is kind of piece this information together to determine which signals, or at least depending on the chemical shift, how those signals are going to fit into an overall structure. If we saw these three signals, we certainly know that this CH2 would correspond to being right next to the chlorine because it is the most de-shielded by that chlorine. Okay, so that's inductive effects. The next one is maybe a little more interesting. I don't know if I put a 1 above. Yeah, maybe. All right, so this one we're going to start out calling pi bond effects. So we've seen a table kind of like this. So we'll have ethane, and then we will have ethene. What's the common name of ethene? Ethylene. So then we'll have ethine. So what's that common name? It's acetylene. All right, so the hybridization of carbons is clearly changing as we go down the table here. So we've got sp3 carbons here, sp2 carbons, and sp. And so we've also talked about the S character, right? So percent S character of each of these hybrid orbitals. And so what's the percent S character in an sp orbital?
50.
Yeah, it's 50. And so sp2?
75.
Other way. 33. And then 25, right? Because as we add p's, we're decreasing the contribution that our s orbital makes. And so what's more electronegative? S orbitals or p orbitals? What's closer to the nucleus and fills the pole more? Definitely S. And so when we talk about hybrid orbitals, we're going to have a trend where as we move down and we increase S character, we're going to have increasing electronegativity of the orbitals. And so if we think about these hybrid orbitals pulling on that electron density, what do you think is going to be more de-shielded? Do you think it's going to be this very electronegative orbital or this much less electronegative orbital? Yeah, this is a lot more electronegative, and we would expect that proton to be the most de-shielded. So let's see what the results are. All right, so we're going to use delta. What does delta stand for? That's just our parts per million. So when you see delta, that's corresponding to the signal shift in parts per million. And so let's see, we've seen that this is going to be, this ends up being anywhere between 0.8 and 1.7. Do you think the number is going to go up or down for ethylene? It should go up, right? Because it's a more electronegative orbital, which results in a more de-shielded proton, and so we should see a bigger shift. So that's exactly what we see. So depending on the molecule, you can see anywhere between a shift of 4.5 to 6.5. So then finally we get to acetylene. So throw out a number. What do you think it's going to be? 10. It's going to be around 2.5. Anyone got a problem with that? I got a problem with that. All right, so why? What is going on here? Clearly it is not just an electronegativity trend. There has to be something else going on. Would you like to know what that is?
Yes.
I will tell you. Okay, so the thing that is going on, or the question, or the answer to our question, is anisotropic effects. Yay, another effect to learn. All right, so we're going to learn about anisotropic effects. And so let's think about pi bonds and stable bonds and their differences. So a pi bond, is it going to be held more tightly or less tightly to a molecule? Less tightly, right? It's not between nuclei. They're up, they're kind of flopping around a little bit. And so what we can say is that pi bonds are certainly held less tightly. And so as we try our NMR experiment, as we put our molecule into the magnet, what happens is that these pi bonds flop around a lot more than the electrons that are involved in sigma bonding. And so in fact, they flop around so much that they begin to circulate a little bit. And so when we have electric charge circulating, what else is going to be produced?
Oh, magnetic.
Another magnetic, good grief, right? Another magnetic field. All right, so what happens is our electrons begin to circulate. They dance around, and so ultimately what is created is a new magnetic, another one, right? Another magnetic field. Good grief. That's what I wrote in my notes, but my presentation is just not there today, so I'm trying to get through the info too quick. All right, so good grief. We have another magnetic field. So you don't need to be able to draw this picture. I'm going to spend 5 minutes or so looking over what is ultimately a really, really cool thing that's going on. You don't need to be able to draw the picture from scratch. So those circulating pi bonds create a new magnetic field, and so ultimately that new magnetic field is going to determine how our molecule orients itself in our applied magnetic field B naught. So let's see, we'll look at 3 cases and talk about why we see what we do. All right, so in the first case, we'll look at ethylene. And so we're going to have an applied B naught. And so when we put ethylene into our magnetic field, what we end up seeing is it's going to orient itself in this manner. And so the reason that it orients itself in this manner is because of our new circulating magnetic field. And so our magnetic field, first off, the magnetic field created by the electrons, does it go with B naught or against B naught? Against B naught. We talked about this last time. Always it's going to oppose B naught. And so what it ends up looking like is it circulates in a manner such that the middle of our molecule is magnetically opposing B naught. Now, are the protons in ethylene, are they in the middle of our molecule? They're not, right? And so they actually feel this magnetic field, this new magnetic field, but they don't feel it going against B naught. What they do is they feel it actually being added, right? And so because they're on the outside and they actually feel the new magnetic field going in the direction of B naught, what that means is that these protons are extra de-shielded. Instead of our new electron density shielding our protons, it's actually de-shielding because as the magnetic field is drawn like this, we can see again the protons are on the outside. And so the magnetic field is actually aligned with B naught. So certainly that downfield shift that we see in something like ethylene or in double bonds where it's around 4.5, 6.5, some of it is due to electronegativity of those orbitals, but also a lot of it is due to this extra de-shielding that takes place. All right, so let's talk about acetylene. How is that different? So in acetylene, when we have our applied magnetic field, the way that it orients itself is going to be kind of like on end. It's going to stand on end like this. And so again, we have a new magnetic field created from the pi bonds, and again, the middle of the structure is going to oppose. And so what happens is we end up with a magnetic field where again, the inside is going against, but the outside is going with. Now, from the perspective of our protons, is it the same case as we have in ethylene? Here we see that the protons are feeling extra B naught, right, in that direction. But what about in this case? They're actually feeling this new magnetic field opposing B naught. And so ultimately, it's that the different direction of the new magnetic field that ends up explaining why acetylene is a shift of around 2.5. It is because these protons are now extra shielded by this new magnetic field that is now going in the direction. So because our hydrogens are in the middle here, it is extra shielded. Over here, because they're on the outside, they end up being extra de-shielded. I was asked in 10 o'clock, well, why do they line up this way? It's just the nature of the new magnetic field. That's how we do it. This is very much experimental stuff. All right, so we'll look at one more case. All right, so we'll look at benzene. So again, we'll draw benzene kind of on end like we've done our ethylene. So we'll show it sort of like wedges here, indicating that it's coming towards us. And so we're just going to look at 2 protons. We'll look at these protons on the end. And so like in every case, the middle of our molecule, our new magnetic field is going to line up such that it opposes B naught. So what that ends up looking like is going to be a lot like ethylene. So we're going to have the middle opposing, and then over here we'll come back the other way. And so in benzene, are we going to expect our protons to be extra shielded or extra de-shielded? They are now extra de-shielded, and so, I don't know, in ppm, what do you think the number might be? If they're extra de-shielded, is it going to be high or low? It's going to be high. And it's going to be high because our protons here are extra de-shielded, and so in fact we see in ppm a shift of somewhere around 6.5 to 8.0 anytime we have our protons in an aromatic ring. And again, it's going to be anisotropic effects that ultimately cause these shifts. So you can't just look at electronegativities. But fortunately, it's pretty characteristic. Anytime you see a shift between 4.5 and 6.5, that tells you that you almost certainly have a proton that is connected to an sp2 hybridized carbon. Yeah.
So what's the difference that makes the middle one?
So do you see how the magnetic fields all look the same where the inside is opposing V naught? Right, so here, the inside of our magnetic field is going against V naught, right? And so it's the same thing here, and then the same thing here. And so the difference lies in the fact that these protons in ethylene, they orient themselves on the outside such that they're actually feeling the magnetic field going up with V naught, right? But in acetylene, you can see that it's going to be oriented on end, and so the protons actually feel it coming down and opposing. So here, they're feeling an opposing magnetic field. Here, they're feeling a magnetic field going with. And so we end up seeing two different results. It's pretty nifty. Okay, so that's anisotropic effects. Important stuff. So finally, we're going to move to part D. And so we're going to talk about signal splitting. And so signal splitting is maybe the most complex part of this, but it ultimately gives us some of the best information. All right, so let's talk about signal splitting. So whenever we have a signal, we don't always see just one peak corresponding to that signal. So we don't always see one peak for each signal. Sometimes we see that our signal has been split into multiple peaks. You can see 2 peaks, 3 peaks. There's probably an unlimited amount of peaks that we could actually end up seeing. And so what we refer to that as is we say that our signal is being split. And so if our signal is split into multiple peaks, we're ultimately on our spectrum not going to see one nice pretty peak. We're going to see those multiple peaks. All right, so what do these look like? So if we just have one peak, it's going to look kind of like that. And so we are going to refer to that as a singlet. You'll see that abbreviated as S. Really, really complex. Okay, so we can also see a case where there are 2 peaks. And so what do you think we refer to that as? As a doublet. How do you think we abbreviate it? With a D. All right, so then we keep moving and we get to a triplet. And now, interestingly, we find that the peak areas change a little bit. So in a triplet, we find that the middle peak is right about twice the area of the outside peak. So we're going to explain why that is in just a second. All right, so here we've got a triplet. We move on down, we can see a quartet. So a quartet looks kind of like this. In a quartet, how many signals do these 4 peaks correspond to? Is it multiple signals, or is it still just one signal that's now being split? It's just one signal, and so when we see a quartet, we might see 4 peaks, but we have to keep in mind it's ultimately one signal that's just being split into 4 peaks. We don't have 4 inequivalent protons in this case. And finally, we'll just stop at quintet, but it does keep going. So in a quintet, you end up with peaks that look kind of like this. And so we'll explain why we see the areas that we do. All right, so we have multiple possibilities, and so we call this signal splitting. You might see it referred to as multiplicity. Does anyone want to know why? Sure, okay. Why does this happen? All right, so let me tell you. So let's imagine a molecule. And so our molecule is going to be, we'll draw an ethyl group there to make our protons inequivalent. And so we're going to do an NMR experiment, and we're going to focus on the signal that results from HA. Okay, so let's think about what goes on when we do this experiment. We're going to pulse HA such that all of those HA protons are flipped from alpha to beta. And so let's see. We excite. Is that how you spell excite? No. Is there a C in there?
Yes.
Yeah. All right. So we excite HA HA such that all the alpha are converted to beta. And so let's think about something. All right, so let's just think about HB. Let's think about all these protons. HB, is there both alpha and beta protons in a given sample? Do we have both spin up and spin down? Sure, right? We said it was an equilibrium and it was just about half and half. And so as we pulse our electron, as it goes from alpha to beta for HA, HB is already about 1/2 spin up and 1/2 spin down, right? It's just that equilibrium. It's just how these things exist. And so what that means is that when we pulse HA, there's actually two possibilities. So for a given molecule, when we pulse HA, HB could be spin up or it could be spin down. And so are those ultimately two different environments? Are those non-identical structures? Sure, they are, right? Those are two. We have an HB with one quantum number versus another quantum number. And so ultimately, when we pulse our alpha to beta, we see that there are two possibilities for HB. So because there's two possibilities, we say that HA has two possible environments. One corresponding to the structure where HB is spin up, and one corresponding to the structure where HB is spin down. And so if there's two possibilities, what we end up seeing is our signal being split into one signal that corresponds where HB is spin up, and then the other signal corresponds to where HB is spin down. And so how many ultimate peaks will we see? We would see 2 peaks, right? And so we end up seeing 2 peaks corresponding to those 2 possible environments, and so we refer to that as what? That is a doublet. All right, so let's look at another example, and so we'll tie this together in a nice neat bow at the end. Okay, so our next example, we're going to have 2 HBs. All right, so we've got HA still right here. Again, we're going to focus in on HA. We're talking about the signal of HA. So we have HB here and HB here. Are these HBs equivalent? Do they have the same connectivity? Yeah, we would expect them to give the same peak. And so when I say HB, we're talking about all of the HBs. We're talking about one NMR signal. Okay, so in this case, as HA is excited, what states could HB be in?
You think of what? An E?
I don't actually think that there's an E in what. I was on a roll. All right, so HA is excited. What states could HB be in? And so we could have a case where they're both spin up. What other cases could there be? Yeah, we could have them both spin down, or we could have a combo. We could have one spin up, one spin down, or we could have the other possibility where we have one spin down and one spin up. And so what we can see is there's ultimately 4 possible states, and so there's going to be a 25% chance that this one is existing. There's going to be a 25% chance that this one will be existing. And then what about the middle case? It'd be 50%, right? Because there's ultimately 2 possibilities that could give us one spin up and one spin down. And so so how many different environments are there for our HA to be existing in? 3 possible environments. And so how many peaks do you think we end up seeing? We see 3. What do we call that? We call that a triplet. So we see 3 peaks, and that ends up being a triplet. And it also goes to explain why we see, as we grow in multiplicity, we start to see different peak areas, right? It's because, well, for one of these cases, it's 25%. For another case, it's 25%. But one of the cases is 50%. So we always end up seeing that middle peak be twice the area as the outside peaks. Okay. Now, there's an easy way to remember what those signal areas are going to be. Who's familiar with Pascal's triangle? Yeah, it's just Pascal's triangle. So let's write that down. Peak intensity, or peak area matches Pascal's triangle. And so, what's at the top? What number's at the top of Pascal's triangle? 1. And what's on the second row? A couple of 1s. And so for the third row, we have a 1 here, and then what's in the middle? 2 and 1. Does that correspond to the triplet we just saw? Sure. So we've got triplet, doublet, singlet. Next, we'd have a quartet. A quartet's just going to be 1, 3, 3, 1. That's going to be the ratio of those peak areas. So that's our quartet. When we get to a quintet, we see 1, 4, 6, 4, 1, like that. So on and so forth. If you get bored this weekend, you can keep going. You can show me the triangle that you have at the end of the weekend. Okay, so the peak areas, it just corresponds directly to Pascal's triangle, and so that's because that's the number of states that are possible for each of the possible spin conditions. Okay, let's do an example to get us ready for Monday, because Monday we're just going to spend a lot of time interpreting spectra. I think we're about at the point where we're ready to do that. And also, I want to get out of here because it is my birthday today. So, thank you. First thing out of 10 a.m.'s mouth was, how old are you? So I'll let you guess too. How old do you think I am? 50. Close. 39? I've heard it's 31. I'm turning 30. What did you say?
31.
All right, I'm 31. The hairline says 41. The spirit says 31. All right, let's do an example. All right, so our example. And I'm going to go ahead and draw in all of our protons just because, why not? So this is our structure. Proton there. No one in either section mentioned the fact that it's April Fool's Day. It's still my birthday. I can prove it with ID. Someone's got to have that birthday. All right, so how many protons? We got a lot of protons on here. But the question we might ask is, how many signals would we expect to see? What do you think? All right, so first off, the methyls on the left side, are those equivalent? Yeah, those are. And so here's going to be one signal. We've got our lone wolf signal there. I know the proton is going to be like our blue proton. These are next to a carbonyl group. And so this CH2 and this CH2, are those equivalent? No, because this is clearly not next to our carbonyl group. So that's going to be a fourth signal. And then here's the nice thing about a tert-butyl group. These protons on the end, are they all equivalent? Yeah, we're going to see one peak for all of these different protons. So even though it looks really complicated, it's not. I'm out of color, so I better use this highlight. All right, so we have how many signals expected? 5. So we'll say A, B, C, D, E. All right, so that's B, C, D, and E. And so if we thought about peak areas, all right, what would the number of protons be for signal A? It'd be 6, and then for B it'd be 1, 2, 2, 9. And so that would ultimately be our peak ratios, right? If we integrated, that would be what we ended up with. And so importantly, I want to talk about the splitting or the multiplicity. All right, so when we look at signal A, we know it's going to integrate to 6 protons, but what's the splitting going to be? How do we figure that out? We look for neighboring protons, right, that would give a different signal. And so let's just pick one of these red protons. Is there a proton in a next carbon over? Yeah, there's the blue one. How many are there? There's 1. And so here's how we always keep track of how this works. Importantly, we follow the n+1 rule, where n equals the number of protons on a directly neighboring carbon. And so since on the directly neighboring carbon to this methyl group, we see that there's this carbon and there's 1 proton, how many peaks are we going to end up seeing according to the n+1 rule? 2 peaks, and so we would call this what? Singlet, doublet, right? So this would end up being a doublet. So we would see a doublet that integrates to 6 protons. Then what about our blue proton B? All right, so how many protons are on a neighboring carbon? 6, right? Because there's 2 methyl groups. And so according to the n+1 rule, what would we end up seeing for the multiplicity? 7 different peaks. And so we refer to that as a septet. That is what you would see. You'd end up seeing 7 peaks. It would only integrate to 1, but you would see 7 peaks corresponding to it. So it would be pretty fancy looking. We would have, this one would look like this, but ultimately this one that would be a lot smaller would look something like that. All right, what about signal C? What would its multiplicity be? Yeah, so we can see that the D protons are 1 carbon open. There's 2 of them, so according to n+1, we would expect a triplet. And that is what we see. And then the D protons, how will they split? Yeah, also a triplet, because if we count to the right, we see we've got a quaternary carbon, and so there's no proton. So again, we have a triplet. And so finally, we get to our huge, massive peak that integrates to 9. And so what will the multiplicity be? Well, if we count 1 carbon over from here to here, we've got that same quaternary carbon. Are there any neighboring protons to split it? There's not, and so we end up with just a huge, massive singlet for that peak E. Okay, so we're going to basically spend all of Monday interpreting spectrum, and then lab as well next week, and then the next week. So, have a good weekend. Thank you.